I want to start by solving another example problem. Before we move on to some new material. So here's a problem. I believe it is in the homework. We have this system that has a tank on the left labeled A and an open cylinder on the right labeled B. The open cylinder is open above the piston to atmospheric pressure, P naught. And then we have the data that is given there. So we know in this tank A, there is argon. We know the volume of the tank is 400 liters. We know the pressure in the tank is 250 kilopascals, and we know the temperature of this argon. And then we have another piece of information about cylinder B, and it is that we are told that initially that piston is sitting at the bottom, and it takes 150 kilopascals to lift it. And also that this cylinder is empty initially when the process begins. So those are the initial conditions. And then we're told that the valve that you see at the bottom is open so that argon can flow from the tank A to the cylinder B. And it will keep on flowing until the pressure is 150 kilopascals everywhere, and the temperature is 30 Celsius everywhere. So argon is going to go from tank A to tank B. And at the end of the process, everything, or the argon, will be at 150 kilopascals and 30 Celsius. So that's our problem. And then the question, what we're asked to determine, is the work done by the argon. So where is the work being done? Say that again? Lifted the piston. So that's essentially the only place where work is done, and it's of the type that we were looking at on Tuesday. So what should we pick our system to be? There is a better answer.
Just the argon?
The argon, right? The argon doesn't matter what it is. So you don't have to specify the devices themselves. Because if you take everything, you have to be careful. If you take everything, then it might be that the work is inside the system, so it'll be inside your system. You will be able to compute it. So the best system is the argon. All right, so how can we tackle this problem? What can we try? What can we try? If you want to start doing something in this problem, what could you do first? Yes? You, right there. Yeah? What would you do to get going?
To get what?
To get going. Solving the problem.
Possibly like PV equals PV.
Possibly say that again?
PV equals PV.
And what is that?
Like you know the initial pressure and initial volume.
PV equals PV. Well, yeah, PV is equal to PV.
So that you can find out the change in the piston. You want to know the two volumes, how the volumes change.
Okay, but even before we try to do any calculations, how about lady right there? Before we do any calculations, what can we check? No? And the lady right here? No. Anybody? Yes?
Table to see what's happening in the first cylinder?
What table? Is there an argon table? There is not an Argon table in the back of the book. Any other ideas?
Look up the gas constant for argon.
And what?
The table. There's a table.
Okay, I can find the gas constant for argon. That's in the back. What?
Draw force diagram.
You could do that, but we already done that.
Find the mass of the argon
How?
using PV equals MRT.
Can I use PV equals MRT?
You just have to use a different R constant.
I'm sorry?
You have to use a different R constant.
Well, we will use the R that he was talking about, the R for argon that we can get in the back of the book.
Yes, because you're at about room temperature and a realistic pressure.
The realistic pressure. Okay, so you're now getting in the right direction. First thing you can do is say, well, can I use the ideal gas law? PV equals MRT, for example. And in order for you to determine if you can use the ideal gas law, you have to check what he's talking about. You have to check temperatures and pressures and see where we are in order to go ahead. So in this case, for example, I look at my pressures, and I'm told that at the beginning I have 250 kilopascals, and at the end I had 150 kilopascals. So what you can do, which is also in the back of the book, is you could look at the critical pressure for argon, and if you do that, that's that number on the right at the bottom, 4.9 megapascals is the critical pressure for argon. That's in the tables. Since my pressure is significantly lower, my range of pressures are significantly lower than critical pressure, then it is safe to use ideal gas law. That would be the answer to my question. What's the first thing you should do before you tackle this problem? So we determined that we can use ideal gas, and then we write PV equals MRT. We take the R for argon from the back, from the tables, 0.208 kilojoules per kilogram Kelvin, and we are all set. Because if I look at this equation, initially, before the process begins, I have the pressure, I have the temperature, and I have the volume, right? Pressure, temperature, and volume. So I have everything I need to use this equation to get the mass. All right. So let me address your answer. You said PV equals PV. What you really meant is P1 probably. P1 V1 equals P2 V2. When is that true? When is P1 V1 equals P2 V2 for an ideal gas? When is that true? When is that true? Assuming that the mass is constant when the temperature is constant, right? So only for a constant temperature process can you say that P times V is a constant, right? Okay, so which is not the case here, of course, because initially the temperature is 30 Celsius. Well, I'm sorry, at the end it is 30 Celsius too. So maybe that's why you said it. So that's not going to help us to find the mass, though, right? So, okay, so get the mass. That's straightforward. So you just solve for mass. Mass of argon is PAVA over RTA. I'm going to show you the solution of the problem without plugging in too many of the actual numbers, just solving it in symbolic form. So I got the mass, and of course, since my system is the argon, the final mass is the same. There is no change in mass. This argon is a closed system. So I can then rewrite the equation for the final state. Is the same equation. So P2 V2 equals MRT2. And again, what you said would work because the temperature is the same. The T1 is equal to the T2. So, and since the mass is the same, this would work as well. So then you can get the V2. I did it this way because I will need the mass later. That's the reason I went through the intermediate step of finding the mass. So, but here I have the final volume. Again, you can get it this way, or you can get it by doing, like he said, P1 V1 equals P2 V2. You would get the V2 out of that. So let's call the volume in the cylinder V sub B. Because what is V2, by the way?
Total volume in both.
Total volume in both tank and cylinder. So if I now say, well, let me label the volume in the cylinder V sub B, then it's obvious that V sub B has to be the total volume that I just found, V2 minus the volume of the tank, V sub A. And all I have done here is I have substituted in the expression that I got back here for V2, which is PA VA over P2. I plugged it in there because, again, I'm not plugging in numbers. I'm just plugging in symbols. But the bottom line is that I have all these numbers. If I want to plug them in to get an actual number, I can do that. But now I have the volume in the cylinder. So now I need to find the work. And how do I find the work? Let's go back to this schematic here. We said the work is the work that is going to be done in pushing this piston up. How can I calculate that work? Leave that there. How can I calculate that work? I'm sorry? Whoops. Second pressure times the volume in the cylinder. Why? Well, what we do know is that work is the integral of PdV. All right, so that's where you want to start. Work, I'm going to show it to you in a second. Work is the integral of PdV, but what happens in this problem? In the cylinder. I'm sorry? Volume is changing. Of course, if the volume doesn't change, there is no work. But what else is happening? The pressure? Does it vary? So here's a good point. Let me actually, before I show you this, let's just draw a little cartoon for what's going on in the cylinder. So there is my cylinder. Let me redraw it here. Here is my cylinder. Let's draw this piston at some intermediate position here. Argon is coming from the line. As this piston moves up, is the pressure changing? Why not?
Because your volume is changing with respect.
The volume is changing.
Pressure
I agree.
is not pressure can't increase.
Why?
Ideal gas law, the temperature and mass are constant.
No, it has nothing to do with the gas law. The gas law. Somebody at the very beginning said, I want to do a free body diagram. And I said, no, we don't need to do that. We already did that. But if you want to answer that question, then the answer is you can only look at it from a free body diagram point of view. So here is the piston. We said there is atmospheric pressure outside. So this force due to atmospheric pressure is P naught A. A is the area of the piston. Here I have P inside the cylinder. I'm going to just call it P times the area. And if this piston has a mass, then there is also another force, which is mg. All right? And that's it. We assume what is known as a frictionless piston, so we don't have to worry about friction on the sides where the piston touches the cylinder. So those are all the forces. So if this piston is moving up in equilibrium, what is the conclusion? Say that again, louder.
Pressure is not balanced, so
Pressure is not balanced?
The forces from top and bottom are not,
If what?
if the piston is still moving.
No, the piston is more, no, that's not true. That's true if the piston is accelerating. But if a piston is moving in equilibrium, right? First of all, it's moving in quasi-equilibrium for us. It's moving very slowly, but it's moving. But if it's moving in quasi-equilibrium, it's moving very slowly. So it is balanced. So if it is balanced, if it is true that this has to be 0, what is the conclusion about the pressure?
Pressure is constant.
It's constant. So we did this already, but I figured I had to do it again because so many of you didn't seem to get it. So the conclusion that we get from that free body diagram that we did a while back is in a situation like this, the pressure inside the cylinder has to be a constant. So if the pressure inside the cylinder has to be a constant, what is the work?
Pressure times the change in volume.
And the change in volume will be
The volume, just the volume.
the volume at the end because the volume at the beginning is 0. So that you gave me the right answer, but I wanted you to explain why. Okay. So, all right. So going back here, this is all here at the very bottom. The work in general will be the integral from 1 to 2 of P dV. P is a constant and is P2, the pressure that we were given. And then delta V is simply the final volume of the cylinder that I called earlier V sub B. The initial volume is 0. So now I went ahead and I plugged in all the numbers, and you get 40 kilojoules. All right? So that's that problem. Does anybody have a question about this problem? Okay, so now let me switch gears. Actually, let me ask you a question first. Let me pull this right here, because I think I have a question that I want to ask you before we move on. So, let's see. Okay, this question is about something we covered probably 2 lectures ago. Here's the question. In the absence of compressed liquid data, so if we don't have available to us compressed liquid data, and we need to find the specific volume of a compressed liquid, but we don't have the compressed liquid data, we only have the data for the saturated region, for the liquid vapor region in the dome. Right? So if that's all we have, and we need to find the specific volume of a compressed liquid, the best approximation is A, use V sub F at the given temperature, B, use V sub F at the given pressure, C, use V sub F at the given temperature and pressure, or D, use the ideal gas law for the given pressure and temperature. So you can start answering now. All right, so 5, 4, 3, 2, 1. Nothing else coming in. So, all right. What is the correct answer? Oh, look at that. Okay, I'm glad I'm asking you these questions. The most popular answer was V sub F at the given temperature and pressure. Is that right or wrong? Okay. So whoever said that's wrong probably answered A. No? Some people answer B. Quite a few answer B too. So yeah, the correct answer is A. Use V sub F at the given temperature. And you might remember, we went over this. But first of all, why is C wrong? C is very wrong because you couldn't possibly find it. If you tried to use both the temperature and the pressure, you couldn't possibly find it because those would be the temperature and the pressure of your compressed liquid. That's not going to match any value in the saturated table. The way to look at that in a figure would be to look at this, which we did a while back. So, whoops. There is my temperature volume diagram. All right. And the red dot is my compressed liquid that I am dealing with. Right? So that's my real state. My real data point is the red dot. Okay? It is at a temperature T2 and at a pressure P2. Right? So obviously, if I try to go into the saturated table with T2 and P2, I'm not going to find anything because there is no such an entry for P2 and T2 because P2 and T2 give me a point that is in the compressed liquid region. So the two choices then, which are A and B, A would be at the temperature, at the given temperature. So disregard the pressure, use the temperature. That would take you from the red dot to the black dot because I'm reading it at the same temperature. I am disregarding the pressure, which was P2. Now I'm reading some value at P1, which is not my pressure, but I'm ignoring that value. I'm just taking the T2, and I'm reading VF right on the saturation line. You can see those are very close. If I do the other one, the other option, which was at the given pressure, where would I be reading? I would be reading right here at that open circle. So that's the value that I would read if I follow my pressure, which is P2, to the saturation line and I disregard the temperature. That's not going to be as good an approximation. You can see it's farther away from the red dot. All right? So those are the three choices, A, B, and C. The correct one is the one where you keep the temperature. And the last one was just, did anybody answer? Did anybody pick the last one? Let me take a look at that. Yeah, some people did. That's completely wrong, of course. The last one was use ideal gas law. Remember, I told you some of you are going to use the ideal gas law with a liquid. So that's 14 people today. All right. Any questions about this? So here is the problem, the typical problem. I have P2 and T2, and I need to find the specific volume. I'm also including here the internal energy because you will very soon need to start looking for internal energies. So, but the approximation is the same. You approximate it as the value V sub F at the given temperature, and if you're interested in the internal energy, U sub 2, you would approximate it as the specific internal energy of the saturated liquid at the temperature. So, all right. Let's talk about heat transfer. And this is just going to be a very simplified summary of heat transfer because it is not our goal in this class to do anything extensive about heat transfer. You will take a heat transfer course later. So, but here's a little summary. For us, what is important is we have a certain system, and in general, we are going to be interested in knowing if there is any heat transfer into the system from the surroundings that I call here Q sub in, or from the system to the surroundings, which I call Q sub out. And in general, we consider three modes of heat transfer. Heat transfer by conduction, heat transfer by convection, and heat transfer by radiation. So I'm just going to very briefly tell you a little bit about each of these modes. What is conduction heat transfer? Anybody knows? What would you associate with conduction heat transfer? Two things touching. Huh? Touching. What about not touching? What about from one end to the other end of something? Huh? Diffusion. Yeah, that's another. Heat transfer by conduction is diffusion, but in what medium?
Heat transfer through a solid?
Through a solid. That's the most common answer, although there can be conduction. In fact, there is conduction through any medium. Right? But typically we associate it with heat transfer through solids. But what it really is the molecular transmission of heat. So we usually think about it through solids, but it can be a liquid, it can be a gas. There is conduction. It's the heat transfer that is associated with molecular activity. So electrons is transmitted, for example, the same way as you transmit electricity. So electron transmission. Now for solids, there is more than just the molecular activity, because the solid is typically arranged in lattices, and those lattices vibrate, and all that transmits heat by conduction. So here's a little cartoon of a medium. If it's a solid, it will be more like you see at the top. So I sketched a bunch of different lattices, and these lattices are vibrating. There is a hot temperature on the left, a cold temperature on the right, and then energy is transmitted by that vibration. Or here you have a little cartoon showing some sort of electron transfer or molecular activity transferring heat from one side to the other. The main law that governs the transfer of heat by conduction is called Fourier's law. And again, this is just so you know a little bit. You're going to take a whole course on heat transfer later on. In fact, probably about a year from now for most of you. So Fourier's law tells us how that transfer takes place. And let me tell you what everything is here. Q is the heat transfer that we're looking into. The double prime denotes what we call a heat flux. So that means it's a heat per unit area. And the dot is per unit time. So this quantity Q has units of energy per unit area per unit time. And we call it a heat flux. And Fourier's law tells us that the heat flux in conduction is proportional to the temperature gradient. So if you have a temperature gradient where the temperature is dropping from one point to the next, then that gradient helps you find the heat flux. And the constant of proportionality is this K, which is called the thermal conductivity. That's all here. So it's a property of the material. As I told you, the heat flux has units of energy per unit time, which in international units would be watts, but then also per unit area, so meter square. Now, what you see here, the only other piece of information here, which is more or less an approximation, is you can always approximate the gradient to some degree of approximation. As, for example, if you have a situation like I have here, where there is a TH on one side and a TC on the other side, you can approximate that gradient as delta T, the temperature difference, divided by the total length that the material has, the thickness of the material. So that's just an approximation, but it's good in many situations. So that's all I want you to know about conduction heat transfer for now. The next mode, if we go back to this figure, is convection. And what is convection?
Velocity.
Velocity of what? Velocity of what? Of that solid that somebody said it. Fluid. Right? So convective heat transfer is associated with what we call bulk motion. This is the macroscopic motion, the one that we can see and measure. Not the molecular motion, because that's taken care of in the conduction calculations. So convective heat transfer refers to the bulk motion, the large scale, the macroscopic scale motion of the fluid. So as you know very well, if the fluid moves, then it can carry energy with it. So I have a cartoon here. If I have some hot fluid on the left-hand side and I put a fan in there and I run it so that it moves the air from the left to the right, where the temperature might be lower, then I'm going to be bringing hot air from the left side to the right-hand side. That's convection. In this case, we refer to it as forced convection because I'm forcing it. I'm making it happen by running this fan to push the air through from left to right. But there is also something called free convection. And what's free convection? What causes free convection? Temperature difference is only part of the story. Huh? Yes, but you need something else. You need a temperature difference for heat transfer to take place. The density difference will only make something happen if there is something else. Gravity. So free convection refers to the motion of a fluid due to density variations in the presence of gravity. Because if you have density variations but you don't have any gravity, nothing is going to happen as far as natural convection. Another name for it, by the way, natural convection or free convection. So here is a very simple cartoon. If I have a hot plate here at the bottom, and this hot plate has air above it, and there is gravity, the high temperature will cause the air close to the plate to decrease in density. So then the heavier air will tend to move down, the lighter air will tend to move up. That's natural convection. I'm moving heat by fluid motion, but I'm not doing anything external, like using a fan or anything like that. I'm just letting it happen in the presence of gravity. So how do we compute the amount of heat transfer? Just like we had Fourier's law in the previous case, we have this other law, sometimes referred to as Newton's law of cooling. Newton's law of cooling. Q dot double prime is the same as before. It's the heat flux in watts per meter square. Now, the way I compute the heat flux, if I have convection, is I need the temperature difference. So I need the high temperature and the low temperature. And then I need this coefficient H, which is called the heat transfer coefficient. As long as I can find the heat transfer coefficient, then I can calculate the heat flux. Again, compared to conduction on the previous page, conduction required me to have this property. I told you the thermal conductivity is a property of the material, and you can look it up. You can go to a table, or you can look it up on the internet, whatever. You can find the thermal conductivity of many substances. It typically varies with temperature. So if you change the temperature, then the conductivity will change. The heat transfer coefficient is a lot more complicated because it will depend not only on the material, on the fluid, but it also will depend on the type of flow. So it's a much more difficult quantity to determine than the conductivity. Right? And finally, the third mode is radiation heat transfer. And what is the main difference between conduction and convection on the one side and radiation on the other side? It doesn't need a medium. Very good. So it's really transmission by electromagnetic waves. I don't need anything in between to transfer energy by radiation heat transfer. If I have a hot object and I have a cold object certain distance away in view, so they can view each other, then there will be radiation heat transfer from one to the other. There doesn't need to be anything in here. I don't need to have a solid in between. I don't need to have a fluid in between. In fact, if I have a fluid in between, it gets very complicated. Because if I have a fluid in between, then that fluid participates in the exchange. Like, for example, the atmosphere participates in the exchange from the sun to the earth. And that participation is quite complicated. But I don't need it. I could still get energy from the sun to the earth without the atmosphere in between. So that's radiation heat transfer. There's the sun, there's the ground. And if you want a simple expression to calculate radiation, this is just one, because really radiation heat transfer is the most difficult of the three modes to calculate. But here's, and you can see, in fact, by looking at this expression, which is already very simple, you can see how it is a lot more complicated than the ones that we looked at for conduction and for convection. Q dot double prime, again, the same thing. That's the heat flux in watts per meter squared. But now I have all these things in this case. There is a constant, which is a universal constant, much like the universal gas constant, called the Stefan-Boltzmann Constant, that goes in there. It has to do with the radiation, with the electromagnetic waves. Look at the temperatures. You still have a temperature difference, hot and cold, but now they are raised to the fourth power. So it's not just TH minus TC as we saw in the case of convection. Now it's TH to the fourth power minus TC to the fourth power. But then you have more things. You have, for example, you could have the emissivity, which is a property of a material, of an object that is emitting that radiation. And you also need a view factor, this A sub 1, 2. It's essentially how much of one object is seen by the other object. Obviously, because if the object is not visible, then there won't be any radiation. So A12 is called a view factor, and it has to do with how much of one object is seen by the other object, say by the receiver, transmitter. But then we can compute it like that. That's for a non-participating medium. If I add the participation of the fluid in between, then it's a lot more complicated. But I just wanted you to have at least some very simple reference on how to do very simple heat transfer calculations. We won't really use a lot of this in our problems, perhaps just a couple of problems during this chapter, but not a lot more than that. As I said, there is a whole course on heat transfer later on. Any questions? Okay. Let's see. Let me take a look here or something. Okay. Okay, so let me summarize what we have so far. Notation-wise, when you're writing work or heat transfer in a problem where there is a process, pretty soon we'll be looking at processes that have several sub-processes. So you may have to do W12, W23, and so on. But W12 and Q12, the notation that we will use. We can also many times be interested in the rates at which work or heat transfer are done. So not the total amount, like we did in the example of the cylinder just now, where we find the total work that was done. We might be interested in another problem in knowing the rate at which work is being done. And of course, that we refer to as a power. And then our notation would be W dot, work done per unit time in watts. And the same thing for heat transfer. You just saw, in fact, expressions using watts for heat transfer. So the heat transfer rate per unit time will also be interesting to us. Now, one very important thing in thermodynamics called the sign convention. Let me tell you a little bit of the history of this. When people started playing with or inventing machines that would deliver power, for example, the heat engine, the steam engine, or any other machine, the idea was, and here is just depicted as a black box. I have a heat engine. This is a machine that I have created that is going to deliver work for me. Maybe because I'm going to have a rotating shaft delivering some work, useful work for me. And usually I don't get that for free. I have to do something. If you were looking at the traditional steam engine, for example, you had coal. You had to burn that coal. That's the heat source. So in a very simple schematic, you can say that a heat engine is something that receives heat from a source and delivers work. All right? So because that was the original intent of this aspect of thermodynamics, then people developed this so-called sign convention. And the sign convention is very simple. Let me put that there. So you can see that, and you can also see this. And it's the signs that we assign to the quantities work and heat transfer. And they are different. That's why it sometimes gets confusing. So when the work is being done by the system, then we consider that work to be positive. And at the same time, when the heat transfer is received by the system, then that's considered positive. The reason for that, of course, is that it makes these two quantities in this cartoon, it makes them both positive. Because this work is being done by the system. The system is this heat engine. Whatever is inside this heat engine is delivering work. So it's doing the work for me. It's positive. And this heat engine is receiving heat from a heat source. And therefore, according to this sign convention, then these two quantities are positive. And that's the reason for the original reason for the sign convention that we still use to this date. So keep that in mind. Work done by the system is positive. Heat transfer received by the system is positive. The opposite, of course, is also true. If the work is done on the system, so if I reverse this cartoon, and I put work going in, and I put heat going out. All right. Oops. So if I change it to this, then of course now this work is negative, because it's, according to my sign convention, is being done on the system. And this heat transfer, which is coming out of the system, is now also negative. So that's the sign convention in thermodynamics. Okay, let me ask you another clicker question that I have here ready for you. Let's see. Computer center screen. Whoops. All right, so what is the definition of reduced pressure? This is from last time, from the last lecture. So I'll start it right now. What is reduced pressure? Is it pressure divided by saturation pressure? Is it pressure divided by initial pressure? Pressure divided by atmospheric pressure? Or pressure divided by critical pressure? And yes, you can look it up in your notes if you have it. Okay, 5, 4, 3, 2, 1, 0. Okay, what do we have? D. Yeah, pressure divided by critical pressure. That was an easy one. Right? That's just a definition. And when do we use this? In connection to what? When do we need this concept?
Compressibility factor.
When we're looking at compressibility factors, what we did in the last lecture. Okay, let's work on another problem. Here's another problem. This problem is similar to a problem in the book, except that the numbers are somewhat different. So that's why I'm calling this a problem similar to problem 3230. Right? It's similar. It's little variations in the data, but conceptually it is really the same problem. So a problem similar to problem 23230. So what do we have here? We have a cylinder with a piston. There is something new here though, and is that this cylinder has stops. So it has like a little surfaces that are sticking out that the piston can rest on. All right. So that's the new part, the new concept here. What do we have here? This cylinder has water, H2O. We know how much we have, 0.1 kilograms. We know the pressure, and we know the quality. So we know the quality is 25%. That means we know that we have a mixture of liquid and vapor in that cylinder. And now we have another piece of information. We are told that we need 500 kilopascals to lift this piston. So unless we have a pressure of 500 kilopascals, this piston is too heavy to lift. So we need that pressure. So obviously that means that initially, when the pressure is 100 kilopascals, that piston is just sitting there. And then we are going to do the following. We're going to start heating up this water until it reaches a temperature of 300 Celsius. And we're asked to find all these things. Let's see. Okay, so find the final pressure, find the total work, and plot the process on a PV diagram. Many times, actually, this is the first thing you should do. At least try to start going on that plot because it will help you solve the problem. So we're asked to find the final pressure, the total work, and to make a plot of the process. So if we want to make a plot of the process, then of course we draw that, some of the information that we have. Pressure versus specific volume. And then I put two data points here, the 100 kilopascal, which is my initial pressure, and the 500 kilopascals that are needed to lift the piston. And the first thing that I should do, of course, is locate in this diagram my initial state. All right, so it is obvious that we're inside the dome. Right? So let's say that I put it, it's 25% quality. Let's say I put it right here. Let's say that's 1. That's my initial state. Okay, so what happens next? Where do I go from 1? Up and to the right. How about maybe up and to the left from this side? Where do we go?
Straight up.
Straight up. Why?
Small EV doesn't change.
Because the volume doesn't change. And why is it that the volume doesn't change? Because we don't have 500 kilopascals to lift that piston. So we're going to have to go straight up. All right? And then what happens? At some point, we're going to reach 500. Yes?
How do you know at 300 degrees C the pressure doesn't exceed 500 kilopascals?
How do I know what? Good question. Why don't? We don't know at this point. Right? All we know is that the final state is 300 kilopascals, but we don't know anything else. Right? All we know is that this process has to start going up. Right? So now, your question is valid. Whether we reach the 500 kilopascal pressure or not, we have to determine that first. Right? So how do I determine that? How do I determine that? See if I have that table here. What would you look for to answer your question? Well, I look for the table. You can answer your own question.
Okay, table B1.
Well, yeah, whatever B1, probably B1, 2. Why am I saying B1, 2? Because I have the pressure, right? So if I go to table B1, 2, and here it is, okay? What am I looking for here? Essentially, I'm looking for the entry at 500 kilopascals, because if I go to the entry at 500 kilopascals, is that visible for everyone? All right, 500 kilopascals. I'm going to read a temperature here. Right? What is this temperature? 151.8 Celsius. Right? That is the temperature. In fact, I'll draw it here. That is the saturation temperature that corresponds to that pressure. Right? That line would look something like this. That is that temperature. What was the number again? 151. I'm going to round it up. 150. I'm going to round it up to 152. Okay, so this is 152 Celsius. Right? Now that I have located that, I can answer your question, right? Because now I know that I'm going to 300. Therefore, I am going to hit that point and reach 500 when I am at 152 Celsius. And since I'm still heating this up, what happens next? I'm still heating this up. Now I reach the pressure at which the piston can lift. So now, lift off, right? That piston starts rising. Remember, all of our problems are in quasi-equilibrium, so everything is happening nice and slowly. So the piston starts moving up. Where does the process line take me? Horizontally to the right, right? So I know I'm gonna let's call this A, this intermediate state here, A. And now I know that I'm gonna go straight to the right. Why? Pressure is constant. We already went through the exercise in the previous problem, right? Free moving piston, pressure is constant. So I'm gonna go to the right. So until I hit 300, until I reach 300 Celsius. So when is that going to happen? Am I going to leave the dome or not? Yes. Yes, because if I don't leave the dome, I stay at 152, right? So in order for the temperature to increase, I have to go past the saturated vapor line and keep going at constant pressure, because I have to stay at 500 kilopascals, until I reach a new temperature line here. Right? We don't really have to draw the whole thing. But this temperature line here is the temperature line at 300 Celsius. Right? And that's the PV diagram. All right, so let's go in order here then. I need to find P2. What is P2? The final pressure. We already answered that question by doing the sketch, right? So P2, the final pressure, is indeed the 500 kilopascals. So that's trivial at this point. Now I need to find the work. How do I find the work? Let me get another piece of paper here. What is the work going to be equal to? Yeah, and this is a good point. When you're doing a problem like this, even though it's obvious in this problem that the work from 1 to A is 0, that's not always going to be the case because the path in another problem might be different. So the total work, you can always split it up into parts. The work from 1 to A plus the work from A to 2. I still need to label 2 there. But of course, the work from 1 to A is 0 because there is no volume change. And what is the work from A to 2? Pressure is constant, so that's nice. In fact, it's P2, right? Times V2 minus V1 or VA is the same, right? V1 or VA is the same. So I'm going to put V1, but it's the same. And of course, I wrote specific volumes here, so I'll need the mass. Yeah. I'll need the mass. Okay. Sorry, so we got P2. Do we have V1? How do we find V1? Remember, we were given the quality, right, at 1. So we can do VF plus X VFG, okay, using the data at 0.1, right? So at 1. Right? That gives us our V1. And our V2? How do I find V2? We know it's superheated vapor, right? So we will have to go to the superheated vapor table, and we know it is at 500. So I go to B13 and look for 500. There is B13 at 500. And then go down to 300 in temperature and grab that volume there, 0.52 to round it up to 0.523. So V2 is 0.523 meters cubed per kilogram, right, at 2. Right? And conditions too. So I have that. And the mass is given. So the mass was given. So now I got everything and I can find the work. And the problem is done. And you cannot see anything. There we go. So that's how you do those problems. Any questions? Yes?
So if the pressure wasn't given at 500 kilopascals, so you couldn't look at the table to see it right there, would you have to use the equation?
If they don't give me this pressure?
Well, if they gave us different value, like 450 or something.
Okay. So your question has to do with interpolations, I guess, right? So suppose this pressure had been 450, he's saying, instead of 500. Everything is the same, right? The only thing that changes is this last calculation. So I would have to go here and see that I have a table entry for 400 and another one for 500, but I don't have one for 450, right? So I do have the temperature of 300 in both cases. Right? So what do I do in this case? In this particular case is the average, because 450 is right in between 400 and 500. So I would just have to average 0.654655 and the number that I gave you for this problem. Average those two because it happens to be right in the middle. If it's not 450 but 425, then of course it's a quarter of the way. And if it's any other number, you just have to do a linear interpolation. Does that answer your question? Okay, any other questions? Okay, let's see. All right, so let's talk about the first law of thermodynamics. Here is another cartoon. Similar to ones we have seen. So let's say I have this tank with a gas. And let's say that I do the following. I have this stirrer connected to this pulley and this mass. And suppose that I can stir this gas really, really fast so that I can generate some heat in it. Okay? So I activate this little stirrer at a very high speed so that it generates some significant amount of heat that I can measure. So what I'm doing, of course, is I am putting work into my system, right? Because I have a rotating shaft that is coming in across the boundary and is rotating and is bringing energy to the system in the form that we would categorize as work. But then, of course, if I stop, and I now let the gas cool down, so the gas which is now heated with respect to the initial state will release some heat, Q sub out, and that'll be the end of the process. So the process has two parts. A first part in which I put work into the system, and a second part in which I allow for the heat to come out. So that I go back to the exact initial state. So the gas is at the end of the two processes exactly where it was at the beginning. And we call that type of a process a cycle. Right? So this is a cycle. So initial and final states are exactly the same. And of course, if I do a very simple energy calculation, and I know that energy is conserved, I would say that all the energy that I put in the form of work must have come out in the form of heat transfer. So it's obvious that W in must be equal to Q out because this is a cycle. The initial and final states are the same. So in general, we can write that like that. So this integral that you see there with a little circle around it is the way we write an integral for a cycle. So the cyclic integral of the work must be equal to the cyclic integral of the heat transfer. That's just a more general way of expressing the same result that I wrote above. In other words, it would be like looking at the work not as a total, but as incremental amounts, delta W, and then adding them all up in an integral. So it's the same thing. And the heat transfer the same. You will be looking at the incremental amounts of heat coming out, and then you add them all up, and that's your cyclic integral. So this statement is a more general way of writing that statement for a cycle. So now let's do the following. Let's consider not this process, but any other process. So suppose that I make a plot like this. Here's a plot of a process, or three processes actually, that I'm going to describe to you. Note that I didn't put any particular properties on this axis. It could be any two properties. So I have some property on the vertical axis, some other property on the horizontal axis, and I have an initial state 1 and another state there 2. And I'm going to do a couple of things here. I'm going to do a cyclic process where I'm going to go from 1 to 2 on a path that I'll call A. Right? And then I will come back from state 2 to state 1, but I'll come on a different path that I'll call B. So forget the red curve for the moment. Just look at the two black curves. And that's a cycle. From 1 to 2, then back to 1. And let's just write what we just wrote. So we have that the cyclic integral of dq must be equal to the cyclic integral of dw, because energy must be conserved. But what I'm going to do is, just like we did in the problem that we just solved when we were calculating the work and we broke it down into parts, I'm going to do the same thing here. I'm going to break down the integral for q in 2 parts, and I'm going to break down the integral for dw in 2 parts. The 2 parts are simply the 2 paths, because I have going from 1 to 2 on path A, and then coming back from 2 to 1 on path B. So this is exactly the same expression, but now broken down into 2 parts. So the cyclic integral of dq, I have broken it down into one integral that goes from 1 to 2, and another integral that goes from 2 to 1. These are not the same, of course, because the paths are not the same. We discussed that last time. Right? So that's why I put A for the first integral and B for the second integral, because they are on different paths. Same for the work. So the first integral on the right-hand side is the work in going from 1 to 2 on path A, and then I add the work going back from 2 to 1 on path B. Again, those are not the same because they are different paths. Okay, so now the red curve comes into the picture. Suppose I redo this, but instead of coming back on the B path, I am going to come back on the, I'm sorry, take that back. Instead of going there on the A path, I'm going to go there on the C path. So I'm changing the going path from A to C, and I'm still going to come back on B. So it's the same thing, except that I'm going on C and returning on B. So if I write that, of course, it looks pretty much the same. All I have done is I have changed the A to a C in the first integral on the left-hand side, and the A to a C in the first integral on the right-hand side. It's the same story. And I did it in red so you could see the difference. So, but it's the same expression, simply denoting 2 different paths. But now I can do something interesting. What do you think I can do?
Make A a flow.
What?
Use the 0 flow to relate.
No, I'm not going to use it. It's a mathematical thing that I want to do next. I have these 2 equations. Subtract them. Right? It's interesting to subtract them because parts of them are going to cancel out. So if I just subtract this, right? If I just subtract this part that relates the integral on the B path is the same, so it will cancel. And the same for the work on the B path. So the B path disappears if I subtract. Just subtract those 2 equations. You got 8 terms, but 4 of them cancel out, so you end up with 4 terms. And they're right there. So now I have the integral from 1 to 2 of dq on path A minus the integral from 1 to 2 of dq on path C equals to those 2 integrals for the work. Now I can rearrange this like this. So in other words, I'm going to move everything that has to do with path A to the left side of the equation, and everything that has to do with path C to the right side of the equation. So now I have this integral here of work on the right-hand side is going to move to the left side, and it is here with a minus sign. And of course, this one on path C on the left-hand side is going to move to the right-hand side. It's now positive. So I have that. And this is interesting because notice that both are integrals from 1 to 2, and the integrand is the same, right? dq minus dw, dq minus dw. The only thing that is different is the path. So what is the conclusion that I reach from here, from this equation? That this quantity that I am evaluating here is path independent, right? Because path A is different from path C, yet these are the same, and these are just 3 arbitrary paths. So what did we learn about, for example, the integral of dqa, of dq from 1 to 2? This integral, just this one here, is path what? Dependent, right? We looked at that last time. Work is a path-dependent quantity. The same goes for heat transfer. Heat transfer and work are path-dependent. But I just found out that this combination is path-independent. Right? So if this combination is path-independent, so that is repeated here. What can I conclude about that integrand? Whatever is in parentheses, just think of it as one thing. Whatever is here in parentheses, don't think of it as dq minus dw. You have something there, integral from 1 to 2 is independent of the path. What is that quantity that appears in parentheses then? What type of a quantity? Huh? No, it's not a constant. And for us, if I go from 1 to A and I evaluate the change and from 1 to 2 and it doesn't depend on how I go from 1 to 2, what am I looking at? Magic word. Huh? No. Anybody else? Starts with a P. Pig? No. Starts with a P. Followed by an R. Property. It is a property, right? A quantity that doesn't depend on the path, right? A quantity whose change doesn't depend on the path is a property. For example, suppose that in here you had dV, the volume change. Right? The difference in volume between 1 and 2 doesn't depend on the path. Right? So this quantity is a property. And of course, that property is none other than the energy of the system. That property that is measured by that quantity is the energy of the system. So now, if that quantity in parentheses is the energy of the system, then of course what I am measuring is the changing energy. As I go from 1 to 2 and I measure the integral of dq minus w, I'm measuring the energy of the system. So that, my friends, if I write it, for example, in that form, is the first law of thermodynamics. I can write it like that, or I can write it like that. The total energy change in the system as it goes from 1 to 2 is equal to the heat transfer. In this case, remember in the sign convention, the heat transfer, if it's positive, is added to the system, and the work is positive if it leaves the system, so that's an energy subtraction, energy that leaves the system. So the total energy change is the heat addition minus the work. That's an equation that represents the first law of thermodynamics. All right. Let's do a couple of things here. Now, what is that energy? What is that energy? It's simply the sum of all energies. For us, the most important, we also call it the total energy. And for us, the most important energy in a system will be the internal energy that we talked about already. So when we look at this quantity, total energy, which is an extensive property of the system, we are including everything. Most notably for us, internal energy, kinetic energy, potential energy, but we can add any other form of energy that the system may have. Now, practically speaking, in terms of solving problems, most of the problems that you're going to solve, by far, the internal energy is the most important one. Probably 90% of the problems that we will look at the only form of energy that we need to worry about is internal energy. In a few problems, we'll have to worry about kinetic energy, but those will come later. All right. Does anybody have any questions? All right, let's do one more thing here then. What happens if I have a mixture of liquid and vapor? Then the same rules that we use for specific volume apply. So if my system is a mixture of liquid and vapor, every calculation that we did already involving specific volume Vf and Vg can be done with internal energy. So if my system has both liquid and vapor, its total energy will be the sum of the liquid energy and the vapor energy. And I can break it down into specific internal energy for the liquid and specific internal energy for the gas. Multiply them times the mass. Use the quality in the same way we did it for the volume. So any calculation that you could do with specific volume for a liquid-vapor mixture, you can do it also for a internal energy of a liquid vapor mixture. Only thing to keep in mind is that the same care must be taken as to whether you're dealing with capital U, which is extensive, or lowercase u, which is intensive or per unit mass. All right, I will leave it there and see you next week then.